Hello, this is Dr. Fife again. So from section 4.5 is another method for using undetermined coefficients to solve higher order linear non-homogeneous ODEs with constant coefficients. It's very similar to 4.4, but it uses something called the Annihilator approach and the derivative operator. So here we're going to learn how to write an ODE with constant coefficients as a linear combination of the differential operator with respect to y is equal to g of x, which is our non-homogeneous expression, where the differential operator d, capital D, is the derivative, in this case, of y with respect to x. So the derivative with respect to x. We're going to choose an annihilator, a of d, so an annihilator function, so that when you apply a of d to g, you'll get 0. So it's called an annihilator function because it's going to take whatever function you have and it's going to apply an operation in terms of derivatives so that you end up with 0. It's going to annihilate that function g. And then we're going to form this annihilator function times a linear function gives us 0. We're going to use added roots multiplicities to determine the form of y of p. And then once we have the form of y of p, then we're going to solve the same way that we did in 4.4. We're going to solve for the coefficients. And we apply superposition when g of x is the sum of basic types. So our basic idea is to express the ODE as a function of the differential operators L of D applied to y equals g of x. So we're going to rewrite the left side in terms of differential operators. For example, y double prime minus 3y prime plus 2y. So remember, the differential operator gives you a derivative. So y double prime is the second derivative. You're going to write that as d squared. And then y prime is the first derivative. So we get minus 3 times the first derivative, and then plus 2. And then those derivatives apply to the y. And then we have 2 times y. Oh, that type equation there should not be there. We're going to find an annihilator, a of d, for the forcing function g of x, where when you apply that annihilator function to g, it's going to give you 0. And then we're going to apply that annihilator function to both sides so that the left side is going to be the annihilator function times that linear function. In this case, d squared minus 3d plus 2y. We're going to solve that higher order homogeneous equation, and then the new roots or increased multiplicity beyond those of the L of D determine the terms that must appear in y sub p. If L and A share a root m, the multiplicities add. Multiply the corresponding piece of y sub p by x to the k, where k is the needed power for independence. That's similar to what we did before. So here's a small table of annihilators. If you have a constant, or if you have 1, or if you have x to a power, you're going to use d raised to m plus 1, or just d to the first the first derivative would annihilate a constant or would annihilate 1. The derivative, m plus first derivative, would eliminate a polynomial of degree m. E to the ax can be eliminated or annihilated by d minus a. X to the m times e to the ax can be annihilated by d minus a to the m plus 1 power. If we just have a simple cosine or sine, those can be eliminated by d squared plus b squared, where b is the argument of that cosine or sine bx's. And if you have a combination of exponential and sine or cosine, e to the ax cosine bx or e to the ax sine bx, you would use d minus a squared plus b squared to annihilate it. So the superposition approach says if a annihilates g1 and b annihilates g2, then a times b annihilates g1 plus g2. So our basic procedure, let me zoom out just a little bit. We're going to solve this L of D applied to y equals 0 to obtain the complementary solution. We're going to pick the annihilator function a of d so that a of d applied to g will give you 0. And then we're going to apply that annihilator function to the left side of the equation, and that'll give us a new equation, but a new homogeneous equation to solve. It includes the functions that you need to annihilate the g. And then we're going to find the function that is needed to form y sub p. And just like in the last section, we're going to substitute y sub p into the equation and solve it, the original equation, and solve it to get our particular solution. So the difference is, in the last section, we were guessing the form of y sub p. In this case, we're going to use that annihilator function to tell us what that form should be. And here's an example. This should be e to the 3x on the left side. But the first thing we want to do is we want to identify L of D. Let me fix that. L of D. And that corresponds to this left side of the equation, and it gives us d squared minus d minus 2 applied to y. I'm going to factor that because the factors are helpful. D minus 2 times d plus 1 applied to y. Now, this d minus 2 times d plus 1, this corresponds to, I'm just going to get a little bit thinner pen, that if we had let y equal e to the mx, then our characteristic equation would, for the homogeneous equation, would have been m squared minus m minus 2. Notice how that looks a lot like d squared minus d minus 2. So you can consider that differential operator, the equation that comes from it, looks a lot like that characteristic equation. And you could, from here, we know that if d were a constant, we would get d equals 2 and d equals negative 1. And d equals 2 would give us y sub 1 equals e to the 2x, and then d equals negative 1 gives us y sub 2 equals e to the negative x. So we have our characteristic, or our complementary solution is c1 e to the 2x plus c2 e to the negative x. But we also have this left side of the equation written in terms of the differential operator. So that's first. So the first step, we're kind of doing both. We're writing the left side in terms of the differential operator, and we're solving for the complementary solution. So 2. We want the annihilator function. So a of d. This is an annihilator function that will annihilate 6e to the 3x. And the key here is on that table, if you have e to some power, e to the ax, you're going to use d minus a. So in this case, d minus 3 annihilates 6e to the 3x. If you apply d minus 3 to 6e to the 3x, you're going to get 0. Watch, I'll show you. Here, if I distribute, I'm going to get the derivative of 6e to the 3x minus 3 times 6e to the 3x. And the derivative of 6e to the 3x, you're going to carry that 3 down to get 18e to the 3x. And then 3 times 6 is 18. So notice that a sub d is annihilating the function 6e to the 3x. This is our a sub d is d minus 3. And so we want to apply that to the left side of the equation. And when I apply it to the left side of the equation, it looks like I'm going to run out of room here, but I'm going to zoom in here. And if I write my a of d times my L of d, that gives me d minus 3 times, I'm going to take this factored form, d minus 2 times d plus 1 applied to y. And then set it equal to 0. And what I'm doing is I'm actually applying that d minus 3 to both sides of the equation. And on the right side, it annihilates it. It gives me the 0 on the right side. But on the left side, it gives me this expression. And I know my solutions from here are going to be d equals 3, d equals 2, d equals negative 1, or y, this is going to be my y sub p, is going to contain an e to the 3x. My coefficient is going to be a, plus b e to the 2x, plus c e to the negative x. So next we want to see if any of those terms are already belong to the complementary solution, and we can just discard them. I don't know if I have that written here. So it says the new roots or increased multiplicities beyond those of L of D determine the terms that must appear in Y sub P. So Y sub P if I go to L, I've got D minus 2 and D plus 1. I don't really need those terms. It will just contain this term, A e to the 3x. And then from there, we do the same thing that we did before. We calculate our first derivative and second derivative, and then plug it into the original equation to solve for those constants. So I would say yp prime is 3a e to the 3x, and yp double prime is 9a e to the 3x. So substituting those into my original equation, I get my second derivative is 9a e to the 3x minus my first derivative, 3a e to the 3x minus 2 times y, 2a e to the 3x. And that's going to give me 6e to the 3x. And from here, we solve for a. So 9 take away 3, take away 2 is 4a e to the 3x. So there we know that the coefficients have to match up. 4a is equal to 6. A is 3/2. And our particular solution then is going to be 3/2 e to the 3x. And then our general solution is the complementary solution plus the particular solution. It's C1 e to the 2x plus C2 e to the negative x plus 3/2 e to the 3x. So we'll do another example. We'll do this one right here. Y double prime plus y is equal to sine x. So notice that our L of D we get from the left side of the equation gives us d squared plus 1 times, or applied to y. D squared plus 1, you can't factor it, but d squared plus 1 applied to y. Our annihilator function is a function that will annihilate sine of x. And the function that annihilates the sine of x, sine or cosine, in this case b is 1, is going to be d squared plus 1 squared, or just d squared plus 1. So we want to apply that to both sides of the equation. I'm going to start with this left side that has d squared plus 1 applied to y, and then I'm going to apply, I'll do that in a different color, d squared plus 1. So that's my annihilator function times, we'll call this the left side of the equation, and that's going to be equal to 0. So here, those d squared minus 1s will multiply together to give you d squared, or actually plus 1, applied to y, but d squared plus 1 is going to be squared. And what does d squared plus 1 squared give you? Go back to the table, and here m is 1. A is also, oh, nope, that's not right. Maybe my table doesn't give it to me. But notice that with this, the difference between the e to the ax and the x to the m e to the ax is that you have that additional power. So that additional power is going to give you an x times. And that's the same thing that's going to happen here. With this additional power, we're going to have the sine and the cosine, but it's going to be multiplied by x. So our particular solution is going to look like ax sine x plus bx cosine x. That d squared plus 1 is going to give you a sine x and a cosine x. And then with it being squared, it gives you an x sine x and an x cosine x. That's how this annihilator function works. You kind of have to know what the form of the annihilator function looks like based upon the type of function you have here. So I have my y sub p. I'm going to substitute it in. I'm going to need my second derivative. My first derivative, I'll use a product rule for each term. Derivative of x is 1, so I get a sine x plus derivative of sine x is cosine x, so I get ax cosine x. For my second term, using the product rule, the derivative of x is 1, so I get b cosine x. And then derivative of cosine x is negative sine x, so I get negative bx sine x. And then my second derivative of sine x is cosine x. I get a cosine x. Here, using the product rule, derivative of x is 1, so I get a cosine x. Derivative of cosine x is negative sine x, so I get minus ax sine x. And then derivative of cosine x is negative sine x, so I get negative b sine x. And then here, product rule, derivative of x is 1, so I get minus b times 1 sine x. And then derivative of sine x is cosine x, so I get minus bx cosine x. Here I have some like terms that I can combine to get 2a cosine x minus ax sine x minus 2b sine x minus bx cosine x. That's my second derivative. And I've got y double prime plus y equals sine x. Wow, I didn't give myself a lot of space, so I'll just work here. Y double prime plus y equals sine x. Make sure that's right. Yep. Here's my y double prime. I'm going to just copy that. And paste it over here. Come on. But I need to make it a lot smaller. Plus y. And y is just that ax sine x plus bx cosine x. And that's all going to be equal to sine x. So I'm going to zoom in here so I have space to work. And let's see. My ax sine x terms cancel out. My bx cosine terms cancel out. And that leaves me with 2a cosine x minus 2b sine x equals sine x. So for my cosine x terms, on the right side, I didn't have a cosine x term. So those coefficients have to match up, which tells me that 2a is equal to 0, and then a is equal to 0. And then for my sine x terms, these terms also have to match up. And that tells me that negative 2b is 1, or b is equal to negative 1/2. And then substituting in, this was my y right here, I get y of p is equal to a is 0, so that sine term drops out, and b is negative 1/2. Negative 1/2 x cosine x. And our general solution is going to be our complementary solution. We didn't work that out, but the complementary solution would have been C1 sine x plus C2 cosine x. That comes out from this d squared plus 1 with d squared plus 1. D squared plus 1 gives us sine and cosine x. And so we get y equals C1 sine x plus C2 cosine x minus 1/2 x cosine x. And that's our general solution. So, and this is the last one we have. I usually go through and fix all those exponents, but I guess I was in too much of a hurry. Here, my L of d is going to be d squared minus 4 applied to y. D squared minus 4 factors into d plus 2 times d minus 2. And so we get, if we could solve for d, we would get d equals 2 and d equals negative 2. Or d plus 2 and d minus 2. If you look at what they annihilate, d minus a annihilates e to the ax. So that will give me my complementary solution. This annihilates e to the negative 2x. And d minus 2 annihilates e to the 2x. So there's my complementary solution. C1 e to the negative 2x plus C2 e to the 2x. Now on the right side, I have x e to the 2x. So my annihilator function, for just e to the 2x, that's going to be a d minus 2. And because I have that x in front, that's going to be a square. D minus 2 squared is my annihilator function. And so I'm going to apply that to my L of d, AD times LD is going to give me d plus 2, well, actually, let me do it this way, is going to give me d minus 2 squared times d plus 2, d minus 2 applied to y. And I can combine these d minus 2's to get d minus 2 to the third times d plus 2 applied to y, and then equals 0. So we want to take out the functions that match the original L sub D. So we're going to take out this D plus 2. Well, let me just write this up. We're going to take out a D minus 2 as well. But if I were to write the functions that this annihilates, D minus 2 is going to annihilate, so I'm going to say y sub p is a, I don't know if I should do this, but yeah, I guess I will, a e to the 2x plus bx e to the 2x plus cx squared e to the 2x. You stop 1 degree less than the exponent. And then from d plus 2, we're going to get d e to the negative 2x. But we're going to take out e to the negative 2x and e to the 2x, this one, to leave us with our true particular function. So the particular function, I think I'm going to factor out the e to the 2x, and I have bx plus cx squared e to the 2x. That's going to be my y sub p. I need my second derivative. And we'll substitute it in here. So my first derivative, I'll use the product rule. The derivative of bx plus cx squared is b plus 2cx. That's multiplied by e to the 2x. Plus the derivative of e to the 2x is going to carry down a 2. And so I'm going to multiply what I have inside the parentheses by 2 to get 2bx plus 2cx squared times e to the 2x. And I'm going to combine that. I'll start with my 2cx squared. And then I have a 2bx and a 2cx and a b, all multiplied by e to the 2x. And then I'll find my second derivative. I'll take the derivative of everything inside of the parentheses, and that's going to give me a 4cx plus 2b plus 2c, and the derivative of b drops out, times e to the 2x, and I'm going to get smart this time and just put that there, and then plus the derivative of e to the 2x is going to carry a 2 down, and then each of these terms are going to be multiplied by 2 to give me 4cx squared plus 4bx plus 4cx plus 2b. So there I do have some like terms. My 2b's are like terms. My 4cx's are like terms. And that's it. So I can simplify that just a little bit. I'm going to bring that 4cx squared first. Then we'll do our x terms. 4cx and 4cx is 8cx. So I have this one. I have a 4bx. And then I have 2b, and 2b is 4b. And then I have that 2c, all multiplied by e to the 2x. So we're going to substitute this into the equation. I'll try and do that here. So I have y double prime minus 4y equals x e to the 2x, and we're going to solve for b and c. So here's my y double prime. Copy that. Paste it over here. That's fine. And then I have minus 4 times y. Here's my y. Bx plus cx squared e to the 2x. And that's going to give me x e to the 2x. So let's see what I get when I combine like terms. I'm going to zoom in here. So on this left side, all my terms are e to the 2x. I'm going to combine 4cx squared and negative 4cx squared. Those will drop out. And then this will give me a negative 4bx. So, whoops, negative 4bx will cancel with this 4bx. So those drop out as well. And it leaves me with 8cx plus 4b plus 2c equals x e to the 2x. So I have my x e to the 2x terms, and then I have my e to the 2x terms. On the x e to the 2x terms, I have 8c is equal to 1. C is 1/8. And on my e to the x terms, I have 4b plus 2c is equal to 0. I'm going to solve that for b to get b equals negative 2c divided by 4, and c is 1/8. So I can reduce 2/4 to 1/2 times 1/8 gives me negative 1/16. So b is negative 1/16, and my particular solution then is, let's see, b is negative 1/16, and that's right here. X plus c is 1/8 x squared e to the 2x. So by the way, if you're solving these and after you substitute in, if you see that your terms don't line up right, that you're not able to solve for your constants when you're equating the coefficients, then that probably means your particular solution was incorrect. And you might want to go and see where that particular solution came from. I prefer to use a method from 4.4 rather than the Annihilator approach, but you may prefer the Annihilator approach rather than the previous method of the superposition approach. Common pitfalls are using larger than necessary Annihilator. Remember, you have to remove those functions that match the ones in the complementary solution. And forgetting that multiplicities add when L and A share roots. You multiply by x to the k, and we saw that here, that we needed, we had d minus 2 squared, and then we have a d minus 2 here to give us d minus 2 to the third. and then leaving out paired terms. Remember, sines and cosines come in pairs. And that's a brief lecture for 4.5. We'll be back with 4.6.